Section 9.1, we start our discussion of probabilities. Now, probabilities are going to relate back to Section 7, Chapter 7. We're going to be working with percents and with decimals. It's going to relate a little bit into Chapter 6. We're going to be working sometimes with fractions as well. In this section, we're going to talk about how they are determined. So a little bit of vocabulary first. An experiment is an activity whose results can be observed and recorded. You're probably most familiar with experiment being used in a class called science. Yeah, I mean, we do that in science. This is done in statistics a lot, though, too. A lot of things you see with statistical evidence or recordings of things don't really look exactly like science. They're social science instead of being like a biological science or a physical science. But those are called experiments. An outcome is just the possible result of an experiment. Okay, so anything that's observable. So if you decide you're going to go to get your hair cut, one possible outcome is you get a good haircut. Another possible outcome is maybe you don't, right? These are the outcomes, just the things that could happen as a result of your experiment. Your sample space is just a collection of all the different possible outcomes, and it is written inside of curly braces. So for those of you who have taken Math 1, those are not the best curly braces I've ever drawn. This is what we did when we did sets, right? We wrote curly braces and we wrote a collection of objects in between there. So it's the same kind of an idea. An event is just a subset of the sample space. So it's a smaller set of items. So for instance, let's just use a real quick example. Let's say that we're rolling a die. Okay, our experiment is roll a die. You're playing some kind of a game. And in the game, you know, obviously the sample space for the outcomes of the die are 1, 2, 3, 4, 5, 6. Okay? An event simply needs to be a smaller collection of those. For instance, maybe it's evens, 2, 4, 6. Maybe it's primes, which is 2, 3, 5. Whatever. It's just a smaller collection of the events that you already had as a possible set. Okay? Possible collection of events. All right. Theorem 9.1 is called the law of large numbers. It's also credited to Bernoulli's theorem. And it says if an experiment is repeated a large number of times, the probability approaches a fixed number. So this would be the idea of you saying, when I talk about flipping a coin, you flip a coin, it comes up heads or tails, right? Well, what you would say is that if you flipped the coin a large number of times, approximately 50% of the time it would come up heads, and approximately 50% of the time it would come up tails. That's what Bernoulli's theorem says. Now this doesn't work at a small number of cases, okay? So some of you may come from large families. I know a family who has 6 children. So if this were a large number, you would assume that they might have 3 boys and 3 girls, and they have 6 girls, okay? So this doesn't work for a small collection of things. It just doesn't even make any sense. But if you were talking about a huge, large number of items, then that would work. This is why you can talk about there being roughly the same number of males as females born in a large population area, right? It's because of this. It's the law of large numbers going on. Now, probability is found by taking the number of items in a particular outcome divided by the number of items in the sample space. So right here, this N of A means the number of items in event A divided by the number of items in the sample space. So back to my idea with my dice. Let's use that one again as an example. Let's say that our event A is the evens. We roll an even, okay? So how many ways can I roll an even? 3 ways. So that would be 3 in my numerator. How many ways total can I roll a die? 6. So this would be a 3 out of 6 or a 1/2 as we reduce chance. Okay, so that's all probability is. So the number of ways whatever we want to have happen can happen, divided the number of ways any possible outcome can happen. Mutually exclusive events. These are events which have no elements in common. And notationally, it looks like this, which I'll explain, both as a reminder for those of you who've had Math 1 and as an introduction for those of you who haven't. The upside down U means intersection, means what they have in common. Jot that down if you've forgotten or haven't seen that notation before, what they have in common. On the right-hand side, that 0 with that slash through it does not mean 0, okay? It means empty set or null set. It means a set that has nothing in it, a collection of nothing in it. You guys have been in class recently enough for you to have heard me describe something like the null set in my house used to be the number of teenagers, or would be the teenagers living in my house. That's not a null set anymore. I have teenagers in my house now. So I can talk about the null set being the infants living in my house. That will work just fine. There are no infants living in my house. So a null set is just a description of something that in your context has nothing in it. Okay? Mutually exclusive events are often confused with people with another one we're going to get to later when we get there. It's called independent events. Let's come back and talk about mutually exclusive one more time, okay? So mutually exclusive just means events that have nothing in common. All right, so in my die example, can you give me two events that are mutually exclusive? Two different rolls of the die that would be mutually exclusive categories. Odds and evens would be a great example, right? You can't be both odd and even. So if event A was odd, event B was evens, then those two would have nothing in common. They would be mutually exclusive. Make sense? All right. Theorem 9.2 tells us that every event A, when we have a sample space S, has a probability between 0 and 1. Every event. Okay? So if you think about rolling a die, right, what's the likelihood that the die is going to come up 1 or even or prime or whatever? Well, whatever it is, it's a fraction or a decimal between 0 and 1. Right? If you think about it in terms of percentages, what you're saying is it's between 0% and 100%. Right? This is why you don't hear the weathermen telling you that there's a 110% chance of rain. It doesn't make any sense, right? No, it's either something between 0 or up to something to 100. We don't have anything outside of those realm. And that's all this is saying, is that all of our probabilities as well will lie between 0 and 100. Okay. Next one, 9.3 says the probability of an event is equal to the sum of the probabilities of the disjoint outcomes making up the event. All right, so that sounds very convoluted. All it's saying is, let's say we did our example of our evens, okay? So this is consider our six-sided die, and we want to know the probability of an even. Well, what I could do is I could find the individual probability of rolling a 2, plus the probability of rolling a 4, plus the probability of rolling a 6. So I could talk probability of rolling the even. When I do that, I say, oh, there's 3 out of 6. Or I could talk probability of rolling a 2. Well, that's 1 out of 6. The 4, it's 1 out of 6. The 6, that's 1 out of 6. And it works the same way. So you can either think of them as disjoint, which means separate events added together, or you can think about it as a collection of events all where you're counting at the same time, and you get the same answer. I've run myself out of space, so I'm going to slide this up just a little bit. I know it's writing on top of other words now, but you saw it before it did, right? All right. 9.4 says if A and B are mutually exclusive, then the probability of A union B is the probability of A plus the probability of B. And union just means joining them together, joining set A with set B. Okay, so joining all even rolls with all odd rolls in the example that we just gave as our example a moment ago. Okay, so finding the probability of rolling even or odd would be the same thing as finding the probability of rolling an even plus the probability of rolling an odd. Yes?
Okay, so which theorem is this going to?
Theorem 9.4. Yeah, that's why I moved the other part up with Theorem 9.3. So if A and B are mutually exclusive, then we have this theorem. Now, A and B are not always mutually exclusive, so I'm going to show you what happens on the next slide when that's not the case. But there's one more theorem right here, Theorem 9.5. If A is an event, then the probability, there's 3 of these that I'm going to write down. Probability of event A plus the probability of event A complement equals 1. So again, some notation from Math 1. A with the bar on it means complement. It means everything not in A. Okay? So if you think about that, what's the probability that it's going to rain or, as long as it's warm, it's going to rain or not rain today? That's 100%, right? Rain or not rain. That's pretty much every possibility right there. It's either going to or it's not, right? Well, whatever it is for rain plus whatever it is for not rain have to add up to 100%. And that's what this is saying. We can take this formula and we can express it like this, or we can express it like this, or we can express it like this. Those are all just algebra manipulations of the first one. In other words, if I know that there is a 0.35 probability of winning a game, then what is the probability of not? Yeah, just 1 minus 0.35, 0.65. That's all that this theorem is telling you. All right, I'm going to do one more slide and then we'll stop for today. These are the probability summaries. So this is just going to be a collection where you've got them all in one place of all of our properties, plus one more that I haven't shown you. The first couple of them, actually I guess I haven't technically shown you either, but let's look at them. The first one says the probability of the null set is 0. So the probability that you will show up at my house tonight and find an infant there, 0. I do not have any infants in my house. We could call this an impossible event. The probability of going swimming outside today, 0, right? It's quite cold out there. My kids got really miffed when we went to the lake at Thanksgiving of why we weren't going to get in the lake. Yes. All right. Another one, similar. Probability of S is 1. What was S, did we say? Sample space. Sample space is the collection of all possibilities. Yeah, I mean, that would be 1. I mean, it's going to be one of them. 100% chance it's going to be one of those of the all possibilities. This is what we would call a certain event. This is what the weathermen don't do, right? They don't tell you 100% chance of virtually anything because there's always the chance that something's going to go a little bit different than they expected. Right? All right, the next one you saw already, it says that all of our other events would lie somewhere on the spectrum of 0 to 1, probability of event A. And this is for any event A. The next one we saw just a moment ago says if A intersect B is the empty set. Okay, so that means that they have nothing in common. They're mutually exclusive. They're disjoint. Then the probability of A union B is the probability of A plus the probability of B. And I'm going to abbreviate, these are mutually exclusive events A and B. So what if they're not mutually exclusive? I mean, that's definitely a possibility. What if we talked about rolling an even, and we also talked about a collection of rolling a 1, 2, or 3? You know, those are not mutually exclusive events, right? So we couldn't just add them together. There must be something else that happens. Well, if the events are not mutually exclusive, I know that sort of looks like a double negative there, right? That doesn't look so great. But if that's the case, then what happens is the probability of the union is the probability of event A plus the probability of event B minus the probability of what they do in fact have in common. These are for any events A and B. Now let's think about that. I always have students that say, well, shouldn't that be a plus at the end? Well, here's what happens. If I count all the evens, how many do I get? 3. And if I count all the items in the set 1, 2, 3, I get 3. And something happened when I did that. I double counted the number 2. The number 2 is counted twice in those two sets. So I have to remove the double count one time. So that's why this is minus the intersection at the end. I don't subtract both of the 2's, right? I just need to take away one of them. So I subtract the intersection one time. The other intersection that was already counted stays counted. So that's what's going on there. And then the last one's the one we just saw. So the probability of event A complement is 1 minus the probability of event A for any event A. And if this feels a little bit like some of the things we did with Venn diagrams and sets inside of Math 1, there's good reason for that. This definitely has that drawback into that section material.